matrix. Okay, and this X is also along with the one that is required to absorb the bias. Fine. And here anyway, weight matrix, what is the dimension of weight matrix? What is the dimension of weight matrix? If this is C cross 1, okay, and this net value is what dimension? Net value is also, what is the relation between net value and O?
O is f of net.
F of net. Okay, fine. So now J is here. Let us start J from here. Why I am writing O minus Q whole square? O is a vector here. Why I am writing in this way? Because we want to do with vector, okay, derivatives and vector formulation. Fine. So what is the dimension of W? What is dimension of W? If X is D cross 1, okay, and then the dimension of W will be
D cross
C
C.
cross D. Yeah. Is it D cross C or C cross D?
C cross D.
Yeah, C cross D. WJI I will write. Okay, or the elements of W. Fine. So this is how we have. Now let us try to write the back propagations. Okay. So let us write the back propagation. Okay, so let's write here. So now what I want is, see, delta O I want to write here. Delta O, how do I define? Any delta means dou A by dou O. Okay, so if I write delta net in delta net, definition, by definition we consider it as dou A by dou net. Fine. So what is the dimension of delta net, delta O? What do you think is the dimension of delta O? Quick answers are welcome. And what is the solution for delta O also is required? It is C cross 1, and then this is O minus T. Is it? But before writing, and it is O minus T, it is very clear. See, now what we are trying to do is, here I want to write the derivatives at each place. Okay, so how I want to write? See, already I have written here dou A by dou O. So I want to write the next derivative, that is dou O by dou net. Fine, because this will help me finally to write any delta net, for example, or any derivative with respect to the last function. Right? Hope this is clear. So now I want to write dou O by dou net. What is this? Dou O by dou net. Can some of you tell quickly based on the discussion we had in the last classes?
F dash.
F dash. Very good. So this is a matrix. F dash will be, how will it be? F dash of net 1. Okay, and F dash of net what? Net C, because it's three-dimensional vector. And zeros here and zeros here. Right? So this is dou O by dou net is F dash. Very good. And what is the dimension of this F dash? C cross C. Fine. So now what I want to write? I assume that here I don't want to write anything. But if I want to write, I can also write here. Okay. So dou net, okay, by dou X. It's not needed in this expression, but if I want to write dou net by dou net, I can write here. So what is that? Dou net by dou X. Some can of you tell?
W transpose.
It is equal to
W
net
transpose.
equal to W transpose. Okay, so these were the identities we have discussed before, or we have derived as well in the earlier classes. Right. So now what I want to write, my objective is to write what? So I have written the gradients back propagated at different stages. But what is my objective in learning this linear classifier? What is our objective? What should we learn?
To find the weights that minimizes the cost function.
Right. To find the weight that minimizes the cost function. So dou A by dou W is what I want. So let me assume that dou A by dou WJ is what I need. Fine. So now dou A by WJ I need. Let me express using the small or local derivatives I have here. So dou A by dou O we have, and dou O by dou net we have, and where is dou WJ? Where is dou WJ? In which of the parameter variable the WJ is there? In net. So I write dou net by dou WJ. Is this clear? Is this fine or not?
Yes, sir.
Yes. So now what is dou net by dou WJ? You remember how did we define, or what did we find it as? Dou net by dou WJ. Dou net is what? Dou net is a vector. Fine. In fact, in numerator, it is a vector in numerator. Okay. So how did we write dou J by dou WJ? You people remember? Say to simplify us, dou net K by dou WJ. How did we write? Is equal to
Xi when k is equal to j.
Xi when K equal to J. Very good. Okay. And now I want to write dou net. Okay. By dou WJ. How do I write? Dou net by dou WJ. How do we write? You want to write in. If you people remember what did we write? So you people have seen, those who have seen previous video lecture should tell. I can write anyway, but you people, those who have seen, I wish somebody to tell. See, WJ we are finding derivative, so Xi only will come. And here we said whenever there is a row vector, yeah, so whenever there is a numerator has a vector, derivative we are writing in a row vector. So I or K equal to J. That means whenever this J takes one of these K, okay, for K equal to 1, K equal to 0, so K takes in fact 0 to or 1 to C. All values K takes, because net has elements net 1 to net K. When K equal to 1, J equal to 1, then it is non-zero. Otherwise it is 0. Like that. This is a row vector. Please note that. And dimension of this we have written it as C cross. If it is row vector, what is dimension of this? Can somebody tell the dimension of this? Dou net by dou WJ.
1 cross C.
It is 1 cross C. Okay, so just a different color. 1 cross C. Right? So now let us bring these things here. Okay, so this is 1 R K equal to J and Xi, and here F dash, and this is what? O minus P. So this is actually, let me write the dimensions with some light color. C cross 1 are the dimensions agreeing? Right. So overall, dou J by dou WJ, what is dimension? This can also be written as dou WJ. Is it not? As we define any delta means it is with respect to the loss function. Okay. So now is this fine? Is it one dimensional or not? Dou J by dou WJ. We can also write this as C F dash into O minus T. How do I write? F dash into O minus T. How do I, what is that? What is that these two things put together? Is nothing but delta net. Fine. So I can write this as, say, one row K equal to J into delta net, fine, into Xi. Can we write like this or not? And this essentially is equal to what? Delta net J into Xi. This is W delta WJ. Is this clear or not? Okay. So after derivative here, so I'm writing here the derivative delta W is equal to, what did we got after the substituting the things? What did we got? Delta net J into what? Xi. Is this fine or not? Is there anything missing here in what I have written? You people are there?
Sir, it's supposed to be delta WGI.
Right, very good. So it's supposed to be delta J, right? So delta J equal to delta net J into Xi. Okay, otherwise it makes not much sense. Okay, so if we want to update any of the element of this, what I'm trying to do here, see if you understand now, you can see a nice analogy. So if I want to update any of the element here, say assume that here Xi is connected to net J. Okay, so here is Jth element and this is ith element. This is Wji. Okay, I want to write delta Wji. What I'm doing now, just to take the error corresponding to here, that is net delta net J, delta net J, multiply it with the input here, that is Xi. Okay, so error at this end, delta at this end, multiplied by input at this end, will give me the weight update for that connection. Is this clear or not? Okay, so this is, so if even if I have a more layers, we will see whether this follows or not. But so far, what you can see here is any delta J equal to net J, delta net J into Xi. Error here into input here. Is this fine or not? Is this clear? Is this clear?
Yes,
Yes,
sir.
sir.
Very good. So now, see, I want to write now completely delta W. Okay, so what should I, so can you give me some simplified version? Delta W itself I want to write now. Given this whole discussion, okay, I want to write delta W. So how do you think I can write? Using this, see what it involves. Delta W involves what and what? Which are the variables it involves?
J and I.
This implies even here I can write, yeah. See, delta W is what? Delta W means the whole W matrix. I want to write derivative. So what will be the dimension of delta W? It's in fact, okay, you can consider dou A by dou W. W is what dimension? W is C cross D dimension. So I want to write all derivatives together. Okay, so what variables now it involves? Can some of you help me or tell me how do I write delta W directly? Given the discussion so far we had for writing delta Wj. No answer?
Summation.
What are the variables in delta W? Yeah, summation and all you can tell later, but what are the variables involved? You tell. That's good enough for me. See, for writing any weight update, error at this end multiplied by input at this location, I said. Error at this end, what is it? Error at this, say, at the rear end is what? For this connection W's. For this W's, what is the error at this end? What is it here, error?
Delta
Huh?
net.
So which are the variables involved in delta W?
Delta net and X.
Delta net and X, right? So since delta W is a matrix of elements and delta W is Wji is equal to delta net J into Xi. So how do you think using these two vectors, delta W and Xi? How do you think it will be? Can you tell what will it be?
So can you please share the screen?
Yeah, I'm trying to share the screen. Okay, but before that, can't you tell? No, so I just try to see in delta net, what is the dimension? What is the dimension of delta net?
C cross 1.
C cross 1, very good. Okay, and then what is the dimension of delta X? What is the dimension of X?
D cross 1.
D cross 1. Okay, so delta net will, how will delta net will be then? How the delta net will be then? No, you can make a guess.
C cross D.
Yeah, that's matrix is C cross D. Okay, fine. I'm able to get it. Okay, now you are able to hear, and I'm sharing the screen. So anyway, we will conclude with this discussion for today. Right. So now, see, what should I write? Delta, the matrix is C cross D. Okay, delta net is C cross 1. Okay, and X is what? D cross 1. So how do I formulate the delta net? Even leaving about the other things, just the dimensions of the matrix, if you see, how should we X here?
X transpose.
Delta net into X transpose. That's all. Okay, 1 cross. So this is how the delta net will be. Delta W will be. Okay, so if you want to update any weight matrix, you just look at the errors at this end, inputs at this end, multiply error vector by input vector, transpose of input vector, and you will be able to update the weight matrix. That's all you need to do in a neural network. Okay, so what I will do is, so this I think should be very clear to you all. So you do it yourself in notes. Okay, so and I would suggest that you send it the assignment also in terms of assignment. So what I would suggest is also do for a 2-layer neural network where you have a hidden layer. Here also exactly same things, how exactly in similar lines what we have done here, we can do there. Not much changes. Okay, only that here there are two weight vectors. One is W2 and the W1, because a weights connecting from input to hidden neurons, hidden to output neurons. Okay, and you have here also exactly say the error in the defined in this way. You write the vectors at each, okay, at each location. So what is the net value? This is net 2. So here you will get actually two nets. One is net 1, other is net 2. Fine. So net 2 delta net 2 you will get here, or dou by dou net 2. Similarly, you write the derivatives here. For say here before going, see this side you can consider it as H. This side you can consider it as net 1. Okay. So hope you see the distinction. This is after applying the activation. This is before applying the activation. And write similarly the whole things. Okay. And then write delta Kj as the weight elements here. Delta J as the weight elements here now. Delta W1 Ji. Okay. So what I would suggest is as an exercise, you people write and get ready by next class. Okay. On the like the weight updates for W1 and W2 matrices. Okay. So, and then we will discuss in the next class more details about the back-propagation, few more details about back-propagation, and then we will move on to computational graphs. Okay, which is computational graphs are very easy means of finding the local derivatives, and from the local derivatives you can easily find the global derivatives. See, what is global derivative and what is local derivative here? Can some of you tell quickly before we conclude the class, just to give a complete picture of what we are doing here. So what is local derivative and what is global derivative? Let us discuss few points before we close. So what is local derivatives here? So if I say that I want to find local derivative here, what is local derivative? Here it is H equal to F dash net. Okay, I want to find a local derivative here. What does it mean? So here, for example, this will have derivative here because from here to here you have got here. So the gradient will come here from here to here. So what is local derivative here? A quick answer is welcome. Huh? What's it?
Do net 1.
Yeah, do. I sorry, I couldn't hear fully. Can you repeat?
Do H by do 1.
Do H by do net
1.
Yeah, do H by do net 1. Sorry. Okay. So what is global derivative here? So or what we consider it as global derivative for net 1. What will be global derivative means dou z by dou net 1. Okay, we consider it as global derivative. In sense it is derivative from the loss function. Okay, we have inputs only here, right? So do you have any quick questions on this? Do you feel that you are comfortable for doing the two-layer network as well? Derivatives for the two-layer network as well? Yes or no? I couldn't hear any answer. Okay, if I don't hear, probably I may need to ask several other questions. Okay, so if I want to do update these weights, how should we go about? Give me some suggestion then.
We'll calculate the local derivatives and multiply them.
If you want to update this W1 weight elements of all W1, okay, so if I want to write delta W1Ji, okay, how do I go about it? First of all, why do we need W1, delta W1, delta W2? Why do we need this? You people are here? Hello?
You're audible, sir.
Yeah, why do we need delta W1?
We want to see the change in the loss function with respect to change in weight values.
For
updating the weights.
yeah, for updating the weights. So if I want to update the weights, W1, if I specifically if we write, okay, W1 Ji T plus 1, updating the weights through what? Updating the weights through
Gradient.
what? Yeah, updating the weights through gradient descent. W1 is a matrix. Okay, Ji is an element of it. Okay, T minus eta times dou Z by dou W1 J. Fine or not? This is how I update, right? So now to update this, what I will start from here. First write dou Z by dou O, which is very clear. And then dou O by dou net 2. Dou O by dou net 2 is what? F2 dash, which is the forward transformation is O equal to F2 of net 2, right? And here what additionally comes is dou net 2 by dou H. Okay, net 2 equal to W2 into H. So dou net 2 by dou H is W2 transpose. Okay, so W2 transpose, right? And then dou H by dou net 1, next one. Okay, dou H by up to H you have gone here. Dou H by dou net 1, that is F1 dash, because the F1 is the activation function here. So using all this, what we can find, why did we rate all these things? Using all these things, what do we get? A quick answer is required for me. For updating W1, okay, element like delta W1 through delta W1, all these were written for getting what?
The global derivative.
If you
Dou by dou W.
to get the global derivative of what? Very good. To get the global derivative of what?
W1J.
W1Ji is fine, but before that, see, I don't get W1Ji directly here, right? Fine, if I want to write W1Ji, how do I write? So assume that I want to write dou W1Ji. Okay, how do I write? I want to write this. How do I write? So I need a sharp answer. I got all this. Okay, I have written all these for getting what?
We multiply them.
Multiply and get what?
Get the derivative of the loss function with respect to the weights.
I want to get delta net 1. That's all right. So these are all written to get delta net 1. Is it not? So these all will give me these Okay, so if I write the back propagation up to here, this will help me to write delta net 1, right? If I get delta net 1 here, what is the advantage? Delta net 1 I have already here. And if I want to write delta W, what do I do? Delta net 1 into delta W1 equal to delta net 1 into what? Into
X.
X?
I.
Is it X? X transpose. That's all.
Transpose.
Okay. So all this I write to get actually dose A by dou net 1. Okay, or delta net 1. So delta net 1 is nothing but dose A by dou net 1. That is the global derivative. Fine. So this whole thing is delta net 1. After getting delta net 1, I use effectively this. So this will become say one row vector of this, and I will get actually like this. Fine. Is this clear or not? Hope this is clear. Okay, if it is not clear, I suggest you to, even if it is clear or not clear, I suggest you to take a 2-layer neural network and try this. Even in, you can see now, even in 2-layer neural network, the weight update is essentially determined by the error at the rear end multiplied by the input values. Okay, on the corresponding connection. Okay, so if you connect X and J, you use the error from Jth hidden neuron, right? So like that. So I hope this is clear. Okay, and if you want to update delta W2, what is essentially it happens? Delta W2 is equal to, what is it? Quickly.
Delta net 2 into H transpose.
That's all. Delta net 2 okay, into H transpose. Very good. Right, very good. Right, that's how you should answer. Fine. And hence, and we get the weight update like that. This is applicable not just to the 2-layer network. Okay, you take 10 layers or 20 layers. Everywhere we can do the back propagation in this way, where we are writing only local derivatives. Okay, see here, do only local derivatives. From this, we can get the global derivative and update the corresponding weights. Okay, looking at the error here and input here. Fine, I am concluding here now. So I request you to work out yourself and come back for the next class. We will see the limitation of back propagation in deep neural networks. Okay, even with this strategy, what impedes us to develop deep neural networks, and we will see what the researchers have done. Okay, so and we will also introduce computational graphs in the next class. Thank you.